The sun rings like a bell. Pressure waves bounce through its interior, trapped, resonating, rising and falling with the 11-year magnetic cycle that drives every solar flare and coronal mass ejection the sun produces. For centuries, we have tracked this cycle by watching the surface, counting sunspots, measuring radio emissions, building our entire understanding of solar activity on what we could see. This week, scientists who spent 40 years listening to the inside discovered that the surface is no longer telling the full story. The magnetic engine that produces solar storms is moving. Cycle by cycle, it is migrating upward, squeezing into an increasingly shallow layer just below the visible surface. The rhythm has not changed, but the place the rhythm comes from has, and no one yet understands why. That matters, because everything that protects modern civilization from the sun depends on understanding that engine correctly. The sun is not gentle. At solar maximum, the peak of its 11-year cycle, the sun erupts. Sunspot counts surge, solar flares increase by orders of magnitude. Coronal mass ejections, billion-ton clouds of magnetized plasma, are launched into space at millions of miles per hour. When they strike Earth's magnetosphere, they produce geomagnetic storms capable of disrupting satellites, GPS systems, radio communications, and power grids. The Carrington event of 1859 was the most powerful geomagnetic storm ever recorded. Telegraph systems across Europe and North America failed. Operators reported receiving electric shocks. Aurora borealis was visible as far south as the Caribbean. In 1859, the world ran on steam and telegraph wire. The damage was memorable, but recoverable. Today, the world runs on satellites, GPS, and power grids that span continents. A Carrington-scale event striking Earth today would induce currents in long-distance power lines strong enough to destroy transformers, massive custom-built units that take 12 to 18 months to manufacture and replace. The estimated economic damage? Between $1 and $2 trillion in the first year alone. In July 2012, a coronal mass ejection of Carrington-class strength missed Earth by approximately 9 days of orbital position. 9 days. No one saw it coming until it had already passed. Our ability to predict when these events will occur and how severe they will be depends entirely on understanding the solar cycle. And the models we use to predict space weather are built on surface measurements. Surface measurements that, according to this week's discovery, may no longer represent what the sun is actually doing inside. The technique that revealed this is called helioseismology. It works the same way seismology works on Earth. Geologists use earthquake waves to map the planet's interior without drilling into it. This is how we know Earth has a liquid outer core and a solid inner core. Not because anyone has been there, because the waves told us. The sun does the same thing, continuously. Pressure waves, called P modes, are generated by turbulent convection in the sun's outer layers. They travel inward, bounce off deeper regions, return to the surface, and produce tiny oscillations in the sun's brightness that can be measured from Earth. The sun has millions of these modes, overlapping, interfering, producing a pattern of vibration that encodes the interior's temperature, density, and magnetic field. If you could compress these oscillations into the audible range, the sun would sound like a low, complex chord. Thousands of notes ringing simultaneously, each one carrying information about a different depth inside the star. The Birmingham Solar Oscillations Network, BiSON, was built to listen to that chord. 6 telescopes spread across 6 time zones, Australia, South Africa, the Canary Islands, California, Chile, Uzbekistan, ensuring the sun is never unobserved. At any moment, at least one telescope has a clear line to the sun. The network has been operating since 1987, nearly 40 years. 4 complete solar cycles. Chaplin has spent most of his career with this data. He was a doctoral student when BiSON's early measurements were being calibrated. He is now a professor of astrophysics, leading the team that analyzed 4 decades of accumulated observations. What they found was not a subtle anomaly buried in noise. It was a systematic trend, clear, persistent, and spanning every cycle in the dataset. Different P modes probe different depths, Low-degree modes penetrate deep into the interior. Higher-degree modes stay near the surface. By comparing how each type responds to the magnetic cycle, the team could map where, inside the Sun, the activity is occurring. In cycle 22, the late 1980s and early 1990s, the magnetic changes extended to significant depths below the surface. The activity was distributed across a substantial fraction of the Sun's outer layers. In each subsequent cycle, the depth decreased. The activity was being confined to a thinner layer, closer to the surface. Cycle after cycle. By cycle 25, the current cycle, the signatures are the most surface-confined in the entire 40-year record. We have uncovered evidence of systematic changes in the solar activity cycle, Chaplin said. Crucially, magnetic activity is becoming more tightly confined near the surface with each cycle. The engine is the same. The engine room is shrinking. And here's the part that changes the picture. The surface measurements, sunspot counts, flare rates, radio flux, do not show this trend. By every surface metric, cycle 25 looks like a normal, moderately active solar cycle. Nothing unusual, but underneath, the structure is different. The activity that produces the flares, the coronal mass ejections, the space weather that threatens satellites and power grids, all of it is originating from a shallower depth than it did 40 years ago. For decades, space weather models have assumed the surface tells the full story. It does not. That is the discovery. And it is not a small one. What does a shallower magnetic source mean for space weather? The honest answer? No one knows yet. A shallower layer might produce more impulsive eruptions, events that develop faster and give less warning time. Or it might produce more frequent but weaker events. The relationship between magnetic source depth and eruption properties has not been established, because until this week, no one knew the depth was changing. The models used to forecast space weather, the models that warn satellite operators, airline pilots, and power grid managers of incoming storms, are calibrated to surface data. If the surface data is becoming a less reliable proxy for interior activity, those models may be missing something. Consider the practical consequence. A geomagnetic storm is detected approaching Earth. Forecasters use surface-based solar models to estimate its severity and issue warnings. If the magnetic source producing that storm is shallower than the models assume, the storm's characteristics, its speed, its magnetic orientation, its energy, may not match the prediction. The warning may be too late or calibrated for the wrong magnitude. This is not a theoretical concern. It is a gap between observation and reality that has been widening, measurably, for 4 solar cycles. Not today, probably not this cycle, but if the trend continues, if the magnetic activity keeps shallowing, the gap between what the surface shows and what the interior is doing will widen. The surface may say the Sun is normal. The interior may disagree. There is a broader implication beyond our Sun. Every habitability assessment for exoplanets includes a model of the host star's magnetic activity, how often it flares, how intense the coronal mass ejections are, how much radiation it produces. Those models are built entirely from surface observations. They are the only observations we can make for distant stars. If our own Sun's surface is becoming less representative of its internal magnetic state, the same may be true of other stars. The habitability models we use to evaluate whether a distant planet could support life may be relying on a proxy that hides long-term changes only detectable by listening to a star's interior. The Sun is the only star close enough for us to listen to, and it is telling us that watching alone is not enough. Here is what the data confirms. Helioseismic data from BiSON spanning 40 years and 4 complete solar cycles shows the Sun's magnetic activity is becoming increasingly confined to a shallow subsurface layer. The trend is systematic, most pronounced in the current cycle 25. The study was published in Monthly Notices of the Royal Astronomical Society in May 2026. Here is what the data does not yet explain. What is driving the magnetic activity upward? Whether the trend will continue? How it affects the properties of solar eruptions? Whether space weather prediction models need to be fundamentally revised? The solar dynamo, the mechanism that generates the sun's magnetic field through the interaction of rotation and convection deep in the interior, is one of the most complex and least understood processes in astrophysics. No computer model fully reproduces the observed solar cycle. The migration toward the surface may reflect a long-term shift in the internal flows that transport magnetic flux. Or it may be the early signature of something that has happened before. Between 1645 and 1715, the Sun entered a period known as the Maunder Minimum. Sunspot counts dropped to near zero for 70 years. The solar cycle did not stop, but it weakened dramatically, producing almost no visible surface activity for the better part of a century. The cause is still debated. The consequences were measurable. A period of colder-than-average temperatures across Europe, crop failures, frozen rivers. No one is suggesting the current shallowing trend will produce another Maunder Minimum. The data does not support that conclusion. But the Maunder Minimum is evidence that the Sun's magnetic behavior can change on timescales of decades to centuries, timescales longer than any single solar cycle, but shorter than the Sun's 4.6 billion-year lifetime. The BiSON data covers 40 years. The trend it reveals spans 4 cycles. Whether it represents a temporary fluctuation or the beginning of a longer-term shift is a question that only more data, more decades of listening, can answer. We have been watching the Sun since Galileo pointed a telescope at it in 1610 and saw the dark spots moving across its face. For 4 centuries, we counted those spots. We measured their positions. We tracked their cycles. We built our understanding of solar activity on what we could see. 40 years ago, 6 telescopes were positioned around the world, in deserts, on islands, on mountaintops, and they began listening instead. What they heard confirmed the cycle. The 11-year rhythm was there, exactly as expected. But underneath the rhythm, something was changing. Slowly. Across decades, invisible to every instrument that only watched the surface. The Sun's magnetic engine is not broken. The cycle continues. The flares still fire. The coronal mass ejections still launch. But the engine is moving closer to the surface, and after 4 cycles of data, the trend has not reversed. We have been watching the Sun for centuries. We have only been listening for 40 years, and what we are hearing is not quite what we expected.